All right, welcome. Today, we are diving deep into one of the absolute cornerstones of industrial automation, the A+B+A-B sequence. We're going to break down, piece by piece, how simple compressed air and a few mechanical switches can get two cylinders to work together in perfect automated harmony.
So think about this for a second. How do you get, say, a clamp to hold apart, then a stamp to come down and mark it, and then have both of them release in exactly the right order over and over again without a single line of code? It's a classic problem in factories everywhere, and the solution is, well, it's surprisingly elegant. It relies on pure mechanical cleverness, not fancy electronics.
So here's how we're going to tackle this. First, we'll set the scene with the automation challenge itself. Then, we'll decode the actual circuit diagram, breaking the sequence into its two main phases. And finally, we'll look at how this awesome logic is used out in the real world.
Okay, before we can solve this puzzle, we really have to understand what we're dealing with. And that means defining the job we need to do and learning the special shorthand that engineers use to describe these kinds of movements.
Let's imagine a really simple factory job. A machine needs to clamp a workpiece tight. That's cylinder A. Then a second tool, maybe a stamp, has to come in and do its job. That's cylinder B. Now, what's absolutely critical here is that the stamp has to pull back before the clamp lets go. The order is everything. Get it wrong and you've got a mess.
And this is how we write it down. It might look simple, but this little code is incredibly powerful. A is our clamp. B is the stamp. A plus sign just means the cylinder extends, it moves forward. A minus sign means it retracts, it moves backward. So A+, B+, A-, B-. That perfectly describes our whole clamp and stamp operation.
All right, let's get to the good stuff. We're going to look at the blueprint that makes this whole thing possible. It's time to meet the key components that are going to execute our sequence.
So here it is. I know this diagram might look a little intimidating at first, but don't worry. Just think of it like a roadmap for compressed air. We're about to follow the flow step by step from the very start of the cycle all the way to the end.
These are the stars of our show. We have two double-acting cylinders. Those are the muscles that do the actual moving. Each one has a 5-2-way valve that's kind of like its brain. It directs the air to either push or pull the piston. And here's the really crucial part. We have 4 roller-operated valves. Think of these as physical sensors or tripwires. They're the ones that tell the system when a cylinder has hit its mark.
So what exactly is a double-acting cylinder? Well, it's pretty simple. It's a piston that can be pushed in two directions using air. You apply compressed air to one side to push it out, and then you apply air to the other side to pull it back in. It gives us powered motion for both extending and retracting. Okay, here we go. We're kicking off the sequence. Now watch closely how the very first action automatically sets up the trigger for the next one. It's like setting off a line of mechanical dominoes. And we're off. Air flows to the main valve for cylinder 1A. That valve shifts, sending a powerful burst of air to the back of the piston. This drives the cylinder forward, moving it away from its home base at switch 1S1 and all the way out towards its fully extended position at 1S2.
Now this is the magic moment. As the piston rod of cylinder A gets to the very end of its travel, it physically bumps into and presses down on a little roller valve, the one labeled 1S2. This isn't some fancy electronic sensor. It's a direct physical mechanical action. And that action is about to open up a brand new pathway for the air.
And there's our chain reaction. That tripped valve, 1S2, now lets air flow over to the main valve of our second cylinder, 2A. This little puff of air is a pilot signal. It tells that valve to shift, which causes cylinder B to start its own journey, extending from its home at 2S1 out to 2S2. See? The first domino has just knocked over the second.
So, both our clamp and our stamp are now fully extended. The job is halfway done. Now the system has to brilliantly reverse the sequence to get everything back to the starting line.
You guessed it. Just like before, when cylinder B reaches its full extension, it trips its own limit switch, valve 2S2. This is our next trigger. The signal from 2S2 zips all the way back to the main valve for cylinder A and flips it back to its original position. Now air gets sent to the front of cylinder A's piston, forcing it to retract.
Okay, we are in the home stretch. Cylinder A, our clamp, is on its way back in, but our stamp, cylinder B, is still hanging out there, fully extended. So what's the final piece of the puzzle that tells it to go home and finish the cycle?
This is it, the final domino. As cylinder A arrives all the way back home, it hits that very first limit switch we started with, 1S1. That final mechanical tap sends the signal that flips cylinder B's main valve, pushing its piston all the way back home. And just like that, the entire system is reset, waiting for the next command. It's a perfect closed loop.
So, we've just walked through that whole mechanical dance. Let's take a second to recap the logic and see why this kind of clever, computer-free automation is so incredibly important out in the real world.
At the end of the day, the logic is just a beautiful cause and effect loop. A moves, which makes B move. B's movement then makes A return, and A's return makes B return. Each step is a direct physical consequence of the one that came before it. It creates a foolproof, endlessly repeatable sequence.
And you know, this isn't just some lab experiment. This exact logic is the reliable backbone of countless machines you see every day.
Anytime a machine needs to hold something securely, do something to it, and then release it in perfect order, you will find this sequence hard at work, from assembly lines to complex molding and part sorting systems.
Really, it's just a testament to some seriously clever engineering. It is a perfect chain reaction. By using the physical movement of the machine itself to trigger the very next step, you create automation that's incredibly reliable and tough. It can work in dirty, harsh environments where delicate electronics might just give up. So there you have it, the A+B+A-B- sequence, a true cornerstone of pneumatic logic. Now that you see how it works, what simple, real-world task could you imagine automating with just a couple of cylinders and some air? Give it some thought. Thanks for joining me.
Please like, share, and subscribe for appreciation and such more learning friends.